let us now look at a slightly more advanced topic, graph sparsification. This is in spirit similar to the notions like graph spanners. We want a subgraph with far fewer number of edges, but retaining some of the properties of the original graph, and if not retaining the properties in exact value, at least in an approximate sense. Okay. And so there are a variety of such sparsifications, and the motivations of course are quite obvious. If you have a very dense graph, that can take a lot of space, but if you can sparsify the graph and still retain some of the properties, you can work with a sparsified graph which has a lot smaller footprint, memory footprint, and you'll be able to scale, you'll be able to solve problems that you could not solve if the graph was given to you in full. Of course, the price you will have to pay is some amount of approximation. But in most cases, especially in big data applications, we can live with such approximations. So now let's look specifically at one form of sparsification called cut sparsification. And here we want to have a sparse graph that retains the cut properties of the original graph. Okay. And let me also point out that we are typically talking about weighted graphs, and so let's say your original graph is the graph G. Okay. We say that the weighted subgraph H is a 1 plus epsilon cut sparsification of the original graph G if the following condition holds for all cuts. So when you isolate a vertex set A as a subset of V, what we are really talking about is a cut in the graph for the following reasons. Suppose you have a vertex set V, this is the entire vertex set V. When you isolate a set A, what you are talking about implicitly is the cut, the edges going from A to outside A, and that's the cut we're talking about. And for every possible cut, and this would mean that there are 2 raised to the cardinality of V number of cuts, and this property should hold for every such cut. The lambda A of H is the weight of the cut between A and V minus A in H. So remember, now we are actually talking about 2 graphs, G, the original graph G, and the subgraph H. So when you specify a cut in either one of these graphs, there is an induced weight of the cut. So let's look at that. So now let's actually look at a specific example. So let's say we have a graph G. Okay, let's say that the edges drawn in blue are the graph G, and let's highlight a few edges, and we'll call them, let's say this is the graph, the highlighted edges form the graph H. So let's give some numbers. So let's say these are the edges, the weights of the edges in the graph G. The weight of the edges in H need not be the same weight as the original graph G. So let's actually provide numbers for that. So let's say the yellow edges have weights. Now let's consider a cut, okay, and let's consider this cut. So all the vertices on this side are A, and the vertices on this side are B minus A. Now in this case, let's look at so let's see what lambda A of H and lambda A of G. These are the two weights of the cuts that we care about. Lambda A of H is the sum of the weights of the cut in graph H. So that's going to be, so in this cut there's going to be 7 and 8, so that's equal to 15. But if you look at graph G, then the weight of the cut is going to be 5 plus 10, 15 plus 20, that's 35, plus a 3, that's 38, plus a 5, which is 43. Okay. So you see that the two graphs have different weight for the same cut. But if we were to say that H is a sparsification, a cut sparsification, in particular a 1 plus epsilon cut sparsification, then for any cut that we take, the weight of the cut in H must be within 1 plus or minus epsilon of the weight of the cut in G. Okay. And so in other words, the weight of the cut in the sparsified graph should be an approximation of the weight of the cut in the original graph G, and this must be, as I mentioned earlier, true for all possible cuts. Okay. So this is what we mean by graph sparsification. So let's look at a technique to perform graph sparsification in the streaming model. Now we're going to I'm mostly going to just talk about the idea here. The details can be found in the survey paper on graph streaming, which will be posted as well. So let's focus on the idea here. So let's say you have a way to obtain an alpha sparsification for one graph, say G1. Okay. And now let's say you also have a way to find an alpha sparsification for another graph G2, and let's say the two sparsifications are called H1 and H2. Okay. Now what you can see is that when you take the union of G1 and G2, so you look at the graph G1 union G2, you can get an alpha sparsification just by taking the union of H1 and H2. So this is basically the point. When you merge two alpha sparsifications, what you get is an alpha sparsification of the merged original graph. So this is one nice property that we have. Which means that if we can somehow construct the alpha sparsification for G1 and then somehow construct the alpha sparsification for G2, and if we have H1 and H2, then we can simply take the union of them and we will get an alpha sparsification for G1 union G2. Okay. So this is one interesting property that we're going to take advantage of. The second interesting property that we're going to take advantage of is composing multiple sparsifications. Okay. So let's say you start with a graph G1 and you construct an alpha sparsification of G1, which let's say, and that we'll call that H2. Okay. And then let's say you further sparsify H2 to get H3, and this sparsification is a beta sparsification of H2. So you take H2, you sparsify it further using and you get a beta sparsification of H2, and let's say that becomes call that H3. Now what we can say is that H3, which is a beta sparsification of H2, is actually an alpha beta sparsification of G1. So we lost a little bit of approximation here in this transformation from G1 to H2, that is alpha sparsification. Then we lost another beta factor when we got to H3. So H3 ends up being an alpha beta sparsification of G1. So this illustrates how we can compose a sequence of sparsifications to get the sparsification of the original graph. So these are two basic properties of sparsifications that we are going to take advantage of. And now let's look at how we can do streaming, but here, in the interest of focusing on the streaming part rather than actually constructing sparsifications, we're going to make an assumption. We're going to make an assumption. This is an assumption based on the fact that there are other works, other papers talking about how such sparsifiers can be constructed. We're going to assume that there exists a 1 plus gamma sparsifier algorithm A that will produce a sparsification of size gamma, which is equal to O of epsilon to the negative 2 times n. So that's just to be clear. We're talking about, so size of the gamma sparsifier is equal to O of n over epsilon squared on a graph of n nodes. Okay. So now, so this is, we are going to assume that such a sparsifier exists. So you have a way to perform sparsification, but the problem is you cannot simply apply this, because you can only apply this in the streaming. I mean, we were limited to the streaming mode. This is a claim. This is this assumes that the entire graph is available for this algorithm A. So this is a centralized algorithm. Centralized classical algorithm, let's say. So now what we need to do is take advantage of these two properties, these merge property and the composability property, and actually construct an algorithm for the stream. Okay. So so here's the idea. What we do is we so the lowest level here is actually representing what we're going to see in the stream. Okay. So this G1, this very first one block, it basically represents some suitable number. Now this is not just one, this is basically what you're getting in the stream, and you're getting a sequence of edges. Okay. And as you're getting an let's say this G1, I mean each one of these, for simplicity, let's say is 50 edges. After the first 50 edges, you are able to store the 50 edges in your local memory. Okay. What you do is you apply the algorithm A on those 50 edges. So those 50 edges will be some part of the graph. Okay. And you apply and you will get basically the you will get a sparsification, and let's denote that as H10, and then so now you have H10. Then you start getting the edges in G2 superscript 0. Okay. And when you've collected all the edges in G2 superscript 0, you again run the algorithm A, and you will get a sparsified version, which is 8, which we denote it as H20. Now when you have these two subgraphs, these sparsified graphs H10 and H20, we know that these two can be merged, and we'll merge and we will get H1 0 union H2 0. Okay. So this will be a sparsification of G11 based on what we have already seen here, the merge property that we have seen before. Okay. And then we will be what we will do is we will be looking at edges in G3. So then we will sparsify G3, we will get H3 0, then you will get H4 0, you will merge and you will get the merged sparsification of G21. Okay, and that's going to be H3 0 union H4 0. And basically these we can call them as H11 and this can be called as H21. Okay. And now once we have H11 and H21, we can then again merge those two. We will get H12, which is nothing but H11 union H21. Okay. So we are just repeatedly merging things, and remember this H itself will be a sparsified subgraph, so that will be able to fit into your memory. The whole graph G may not be able to fit in, but the sparsified subgraph, the sparsifications will be able to fit in. So and then we will continue. So now we have the sparse graph. Remember this G11, and here's something that I forgot to mention. Basically, G11 is the G11 is nothing but the union of G10 and G20, and that's why you're able to take the union of those sparsifications and get the sparsification of the larger graph. So your stream is always in this level, but for analysis purposes you can think of it as constructing the sparsification for larger and larger graphs. Okay. So similarly we'll be so at this point in time when the stream has reached this point, okay, we have basically constructed the sparsification for all of these edges, which is represented by this G12. So we have the sparsification. We continue, and when we reach this point, we would have computed the sparsification for all of these edges as well, which is represented by G22, and then we can put those two together and essentially find the sparsification for the entire set, which is represented by G13. So there is this nice hierarchical way in which we can perform the sparsification, and if we work out the details, essentially what we get in this approach is that we will be able to get a 1 plus epsilon sparsification, where epsilon is some small positive constant, and that sparsification will have size at most, let me write that out, 1 over epsilon squared, O of 1 over epsilon squared n log cubed n. And the details are available in the survey, but for our purposes it will be good to understand it at this conceptual level.